We're now in week 2 of lab exercise 2. And the checkpoint for this week is to simulate the solver for a 24 by 24 or greater grid using no more than 174 multipliers. That's to simulate what the environment you're going to have on the FPGA. There's 174 18-bit multipliers. And to demo at least a 10 by 10 linear solver, in other words, what you debugged last week in Model Sim, should now be embedded on the FPGA and produce sound. So presumably that's going to be on the FPGA and either running a busmaster under the control of a busmaster, or sending data back to the HPS, which will then feed it back to the audio codec. Any questions on this? So how are you parallelizing for the 24 by 24 grid? Patches, small patches.
Seems easiest.
I would say it's probably easiest. Any other schemes?
What do you mean by patches?
You know, like 2 by 2 or 4 by 4 patches of the drum, as opposed to, say, a row or something of that sort. Okay. So I did, after playing with the audio a little bit over the weekend, which I was doing because I wanted to work on string synthesizers for making, kind of nice sounding instruments. I decided I should change around the organization of the page a little bit so that you could find all the things like the address map and the QSYS layout more easily. So at the very end of the DSP page now is so-called improved string audio synthesis. And the main logical change is a result of something I noticed last week, or helped debug some student projects. And the sine waves that were supposed to be coming out of the solver on the HPS actually looked like this, and they had fuzz hanging off of them. That was amplitude dependent fuzz. And that fuzz was caused by the busmaster running in Verilog that happened to be kind of a ghost left in my audio interface code that was inserting zeros on every n samples. So I went back and disabled the busmaster by adding an extra switch in the reset line for the busmaster, which just said if switch 9 is up on, to hold the system in reset. And then the busmaster does it right to the bus, and all of that interference goes away. So there's a small change in the Verilog, but not very much. But there's Verilog, the zip of the quarters project, the hard to find .h file, QS layout, and then at the end a drum code which is consistent with the environment. So everything's in one place. There's no real change in the logic. It's just all in one place. Any questions on the audio interface? Well, at this point, We are 1 week away from starting Lab 3. Hard to believe, but yes, we're 1 week away from starting Lab 3. So, if we assume that I'm going to talk today about Lab 3, and then Friday will be mode panic day for checkout, and so we'll may cancel lecture, then we have Tuesday and Wednesday, and then Friday will be stone panic next week when the whole thing is due. So we have 3 lectures to talk about Lab 3 before we start Lab 3. So I thought I should start today on the Lab 3 Mandelbrot set. Again though, are there any questions about Lab 2 before I launch into Lab 3? So what I want you to do here in the third exercise is to build a program, build a hardware design that will generate this graphic as fast as possible. And the rule for generating this is that we're going to, for each point on the complex plane, from, let's see, real part is in the range of -2 to 1, and the imaginary part is in the region of -1 minus j to plus j, I believe I've got that right. Yeah. So what we're going to do is say we're going to have some complex number z, and the n+1th iteration, this is also going to be an iterative calculation, like the last calculation. The n+1st iteration will be z of n quantity squared plus c, where all of these are complex numbers. And what we're going to ask is, does this diverge? Does it diverge to infinity? And if the answer is no, then we're inside the Mandelbrot set. And if the answer is yes, we're outside. And the boundary of that set is a fractal, which means it has infinite length in this context. So, how many iterations does it take to diverge to infinity? It can take a very large number. And so we have to bound this calculation in some way that makes sense. Well, there's a condition that says if it's going to diverge, if the magnitude of z ever gets greater than 2, that the system will diverge. You can show that. On the other hand, it might take a billion operations to get greater than 2. So we're going to have an arbitrary cutoff. We're going to have some n max. And we're going to say if it gets greater than n max, that arbitrarily it didn't diverge. What is often used here is 1,000, but that's not unique. So I'm going to have you make that a settable number, with the understanding that as you increase that number, of course, the solution is going to become slower.
So I'm really confused. What the different colors of this diagram mean? What does this actually represent?
It's the time to diverge. It's the number of iterations to diverge. Everything in red does not diverge. Everything outside does diverge, and a blue means it diverged in 1 iteration.
Okay. And then
And this happens to be the log of that number. Thank you. So what you're going to do is that for every point on the complex plane, in other words, every pixel on the screen, you are going to set a C equal to the real and the imaginary part of the number mapped into that pixel, and then set Z naught, Z0 equals 0. You're going to set Z0 equal to 0, and then you're going to run this 1,000 times, that iteration 1,000 times, or quit if the magnitude ever gets greater than 2. Then take that number, so the output number, iteration, so some in iteration, you're going to take the log base 2 of that and plot the color. How do you take the log base 2 of a number? It's the position of the high order bit. Let's say we have log base 2 of 0 binary 1 0 0 0. What's the log? 0 1 2 3. Oh, it's equal to 3. So the position of the high order bit is a reasonable approximation of the log. So a priority encoder in Verilog takes the log. You say, well, that's rather crude. What is the next bit worth? About half. But since this only has, since the number of iterations is going to run from 1, being the minimum, to 1,000, then the log will be running from 0 to 10 or so. And 10 colors sounds like about the right number of colors to draw, so why have a finer gradation than 1 log unit? You can go to half log units if you want, but you don't have to. So, to summarize that again, what you're going to do is you're going to iterate this function for every point in the plane separately. For each different C representing one complex position, you're going to iterate this function up to 1,000 times, and then derive a color from the log of that, and plot it.
So I noticed, like, on this graph in particular, like, there's a rectangle bounding kind of a set of points which are totally encapsulated by points which also diverge, right?
Yes.
So is there a way to kind of, like, basically skip points?
Good question. Is there a way to kind of skip points? And the answer is yes, there are. There has been a tremendous amount of analysis on this particular shape. This happens to be the biggest rectangle I could fit inside of the, strictly inside of the Mandelbrot set, and certainly everything inside that rectangle does not need to be checked. You automatically set it to inside.
What about symmetry?
It is symmetric, so anything you calculate up here is also true down here. Good, yeah, that's also true. However, remember that that's only true if you're drawing the whole set. You're going to be timed on this. Part of your grade will be how fast you can draw this. But you'll also be timed on drawing something like that, which will not be symmetric. But for the whole Mandelbrot set, yes, there are a bunch of known features. One is the biggest circle that can be inscribed in here is known. The biggest rectangle is known, that's close to it. The biggest circle that can be inscribed in here is known. The biggest cardioid that can be inscribed in there is known. You know cardioid? Heart shape. Every time you get a more complicated function, though, you have to do a more complicated calculation to see if you're inside or outside of it. So there'll be a trade-off in the number of operations it takes to find out if you're inside of a closed figure versus just doing the iteration. Where's the trade-off? A little hard to say. in general, there may or may not be an HPS to control the calculation. You might want to set parameters by using HPS and then do calculations on the FPGA. You might not want to use HPS and just use the buttons on and switches on the FPGA to directly have a zoom control, because one of the things you need to do is to be able to zoom and pick the center of the region to render and the zoom factor. You're probably going to use a busmaster to compute the image, because I can guarantee that if you send all of the pixels back to the HPS and then have the HPS then write back to the VGA, it will be too slow. Now I'm going to talk about different ways of writing to the VGA, some of which are faster than others. The fastest one I know of requires that you throw away the video subsystem on QSys and write your own. And that sounds daunting, but in fact is fairly straightforward, because you can strip down all the functions you don't actually need for this very specific thing. And one of the students about 3 or 4 years ago did that and put the code up. So there are various ways of writing to the screen, but we'll talk about some of those as the lectures go on. And now you're going to have to write a iterative pipeline to calculate this. It's got to be a complex arithmetic type pipeline. I suggest using 4.23 fixed point, and the reason for 423 is you have to have a dynamic range which comfortably includes the square of 2. So you have to be able to represent 4 and minus 4, and it's not a bad idea to have an extra bit in there in case you overflow. So 4.23 allows you to have a range of plus minus 7 while fitting the whole calculation into one multiplier, 27-bit multiplier. So probably you're going to go for 423. Why 423? Well, it takes about 10 bits of the number to specify which pixel you're going to draw. Remember that the screen resolution is 640 wide. That's just a little less than 10 bits. So you're going to need about 10 bits of resolution to specify each x, and another 9 bits to specify each y. So if it takes 10 bits to specify an x and a y, and you start zooming, you can do about 13 zooms before you start running out of bits to represent the zoomed in numbers. So you can only go down about 13 levels into the visual image. The best solver last year, which was done as a final project, not as Lab 3, could zoom 2,400 times, because they were using arbitrary precision arithmetic. It was dynamic precision arithmetic. I'm not going to require that for this lab. 13 zooms is enough. There's some video out there. This is one of the projects. That's about the speed at which they could calculate new images. This particular piece of the structure is known as Horseshoe Valley. Some pieces of the Mandelbrot Set have names because, you know, people do that. There's some stills of various subsections of the set. An interesting thing is that embedded in this set at every level are things that look like little tiny Mandelbrot sets all down through the edge of the Mandelbrot set. And there are people who spend their whole life trying to find their initials in the Mandelbrot Set. I think I'm kidding. That's a cool one. You can see the pixelation there a little bit, but interesting structures. And some of them have names like Devil's Eye and Alien's Egg, and you know. Oh, that's way down in the center of the set, and that's yet another Mandelbrot-like outline. So the checkpoints are going to be demo simulation of one complex iterator pipeline. And the number of iterations, and the check will be, the correctness check will be that the number of iterations required should match the equivalent MATLAB point in the complex plane for at least a couple of different values. Week 2 will be to demo more than one complex iterator, bus master, writing to the VGA bus slave to show a full Mandelbrot set on the VGA. So now that'll be real hardware running on the FPGA. And then, and also to demonstrate interactive zooming, but probably not full control. At least some zooming. And then week 3 will be the full design. Any questions? Dynamic range of solution speeds is typically enormous in the class. Since we've gone to this architecture, the slowest I've seen is about 2 seconds to draw. The fastest is about 25 milliseconds. So 2 orders of magnitude difference in drawing speed. Questions? Well, let's go to a few more details. So we're going to be mapping the range of -2 less than or equal to the real part of C less than or equal to 1, and -1 less than or equal to the imaginary part of C less than or equal to 1. So that's about a 2 high by 3 wide image. That approximately matches 640 by 480 aspect ratio. It's close enough. So we're going to map this range so that the default Mandelbrot set will have 640 x steps between -2 and +1. And the vertical axis will have 480 steps between -1 and +1. Oh yes. When you zoom, it will be sufficient, because it's nice to have the aspect ratio not change too much. It will be sufficient to click on a point and have the zoom change by a factor of 2 in the X span and the Y span, centered about that point, with the same aspect ratio as the full set.
What, you say click on a point, are we going to be attaching a mouse to this?
You could. You don't have to. You could. The USB port accepts a mouse. We have a bucket of mice in the lab. You can hook it on there. 2 lines of code will read the mouse. So you could click on a point. You could read it, or you could use the 4 buttons on the FPGA as cursor control. Move a cursor, an image cursor, around on the screen until you get to a point. Press another button. There's only 4 buttons. You might have to attach a button. Press a button and say, that's the point. Zoom a factor of 2 there with the same aspect ratio as the main screen.
How do you recommend parallelizing this computation?
Well, that is an interesting. Well, first of all, there's kind of there's a trivial aspect to this, which is to say, every point is completely independent of every other point. The calculation which occurs for this complex point depends on C, but not on the value of any other point. Therefore, you can write an iterator which completely calculates one point and then plots the point. So in that sense, the computation is referred to as trivially parallel. There's no interaction between calculations. The interesting part comes in that each different point takes a different amount of time to compute. Unlike the drum, where each point took exactly the same number of cycles to compute. Here, if you just iterate it, you're going to take 1,000 iterations before you stop. Here, you're going to take 1. And so there's a load balancing problem. Let's say that you've built 10 iterators. How do you assign pixels to the iterators so that they all finish at the same time? That's the question, because if they all finish at the same time, it means they're all fully loaded and you're going to get the fastest possible calculation. If 9 out of 10 iterators finish in a second, and the last one is in the center here, cranking away as fast as it can, it's not finished yet. So then the question comes, how do you decide how to assign pixels to iterators? Do you do it dynamically? You could. As soon as an iterator finishes, you give it the next pixel on the queue. Or in the raster, however you want to say it, right? The next pixel on the list. Or you could say, I'm going to have predefined blocks, and then statically assign those different regions of whatever the magnification is to an iterator, and that's how it's going to work. And then you have to ask, what is the best shaped block so that statistically speaking, they all have about the same amount of work? To a large extent, this comes down to an issue of how fast can you solve a point versus how long does it take to dispatch a point to the iterator. If the dispatch mechanism isn't extremely simple, then it will be slower than a stupid algorithm that just statically assigns pieces of the image to different iterators. In fact, the best solutions I've seen, the fastest solutions I've seen have been static assignment. You just say, this block goes to iterator 25. The next After 4 pixel scan lines go to iterator 26. The next 4 go to iterator 27. It's an interesting question. That's one reason this is an interesting lab. There's lots of design decisions that you can make. And so it's good for a design class because you have to kind of do trade-offs to figure out what makes the most sense to do. Now, I thoughtfully provided you with some C code so you could see one way of doing it. This is also the code that you need to beat. Let's see, there's a link here someplace, but I won't bother with that. If you go down to the university page, university program page, there's Mandelbrot Set on VGA HPS 8-bit color. Oh, yeah, you can't use black and white. You have to have at least a few bits of color. 8 bits is enough. You don't have to have 8 bits. 4 bits is enough. Why does this matter? Why am I specifying the number of bits? Who's got an idea?
Just convert the log into the color directly.
You could do that? Yes, you could. On the fly. You don't have to store anything but the log. That's right. And that's very efficient. In fact, you can do it in much less than 1 cycle, so it's efficient enough. The main reason is the way to get speed, of course, is parallelism. If you're going to have parallel solvers, you've got to have parallel memory accesses. If you're going to have parallel memory accesses, it means using RAM internal in the chip, and that's a limited resource. So the fewer bits of color depth you can use, the more resolution you can put on the screen. It turns out you can do an 8-bit color image in on-chip memory on the FPGA, but you cannot do a 16-bit image. So I would say 8 bits or less will allow you to be in static on-chip RAM.
Actually, that brings up a good question. How do you write to the VGA for multiple solvers in the same cycle?
Well, that's a different question, right? You can't write to the VGA from different solvers on the same cycle. Unless you write your own VGA controller. So let's say you have, this is down in the weeds a little bit now, but since you asked, let's say I have 4 solvers, 0, 1, 2, 3, arranged as stripes across the screen. And you could argue, should the region, if you do static allocation of pixels to solvers, should you do long stripes or compact regions? What do you think?
Long stripes are going to balance your load better, because if you do a compact region, you're going to have a region which is entirely inside the Mandelbrot set and a region which is entirely outside of it.
That's right.
But a long stripe will cross in and out.
And long stripe will statistically cross more boundaries than a compact region. So because it's got more edge, right, per unit area. So let's say that we used 4 memory blocks. So solver 1 writes to memory. Solver 0 writes to memory 0. Solver 1 writes to memory 1. Solver 2 writes to memory 2. And solver 3 writes to memory 3. No conflict. Done. Right? No conflict. No write conflict, no wait states. Then the custom VGA controller, muxes, geez, that's horrible. Let's try that again. Muxes off of those 4 in order. And And since the VGA draws in serial order from top left to bottom right, there's never a conflict between memories. So it's dual ported memory. This port is a write port, this port is a read port. There's no conflict between read and write because the memory is truly dual ported. So you have to mux the VGA controller on this side to know which block to read from, so you have to use a custom controller. But this means that you can write with absolutely no memory conflicts.
But then, how does the VGA controller know which pixels inside the node bus should actually be writing to the screen?
Oh, it has an address. So the VGA controller that you're using now reads static RAM. Dynamic RAM, SD RAM. It issues an address to SD RAM. SD RAM gives it back a color, which it then puts on the screen. What you're going to do here is you're going to produce an address. The VGA controller that you're going to be using produces an address that you write, produces an address, 2 bits of which will determine the muxer, and the other bits will determine where in the image it is within that stripe. So you'll give it a 19-bit image, a 19-bit address, or 20-bit address, and what will come back through this muxer is a color for the pixel you need. VGA runs at 25 megahertz, 25.125 megahertz. You can't wait for the pixel. VGA has no memory. It wants the color when it wants it. And that's the huge advantage of the dual ported memory, is the controller can read the memory anytime it wants. C code. So we've got, I bothered to do a little bit of optimization to see how much it mattered. No optimization yields a 0.91 second execution time. Op3 yields about 3 times faster. What I found most interesting, though, was that fixed point was twice as fast as floating point, even though this machine has floating point hardware. And I believe that the reason is, although I'm certainly willing to be called wrong on this, I believe the reason for that is that the ARM core we're using, ARM v7 core, is a limited dual issue core. It has dual issue on the integer unit, but not on the floating point unit. So you get 2 fixed point instructions on every clock cycle, but only 1 floating point instruction. Could you do all 3? Probably. But there's also a so-called neon vector coprocessor on the HPS, which I haven't tried to get running yet, but it does vector arithmetic in an arithmetic coprocessor on the core. So what the code does, overall code, is it generates some X increments, and this is just, it's all floating arithmetic, so we're doing we're calculating a float number between -1 and -2 and +1, and then we're fixing it. We're doing a float to fix 28, and I printed this initially so I could make sure I wasn't doing something stupid. And then same thing for the y-axis. Then we do a get time of data to estimate the time. these are estimates of where the biggest circle is that you can put inside the Mandelbrot set, so I could optimize away the calculation for every point inside. And then you just brute force calculate. You set the C equal to the real and the imaginary parts as per the algorithm. I'll show you an optimization that cuts down the number of multiplies somewhat, and that's what these squares are for. And then we detect the secondary circle, the secondary bulb, and the main bulb to see if this is trivially inside the set. And if it's not inside the set, then we iterate. While count is less than max count, grind through it. Calculate the imaginary part, calculate the real part. Square them both. See if the product is greater than, I love the way this broke down, 4 fixed 28, so that's the number 4. Because you never take a square root, you always just compare the square of the distance to the square of the magnitude. And then this is my log function. And in Verilog, it's actually easier to do the log function than it is in C. So you probably want to run the C code, get a feeling for it. This C code with the fixed point runs in about 0.85 seconds or so. So that's the time you have to beat. You have to beat that. So now how do we actually put this into hardware? I think I should wait till next time for that. Are there any questions? The nice thing about graphics is you can tell when it's right. It looks right. And there are various features that you can see in some of the projects which suggest certain kinds of artifacts. So you notice that these contours out here are all nice and smooth. Now let's take a look at a couple that were calculated in Verilog. Calculated in Verilog. Let's look again at this one. No, not that one. I want a still. This is slightly different, but still pretty scalped. It's monotonic. You don't see any weird lensing out here. Little regions of color that are lens shaped. Let's see if we can find one. There's one that doesn't look monotonic. It's got these weird lens shaped things, although near the set itself it looks okay. What do you think causes that? It's an arithmetic problem. It's overflow in the squares, the sums of squares. So when you take the sums of squares, either square could be up to 4, just slightly less than 4. The sum of them could be slightly less than 8, which is bigger than the maximum number you can represent, and therefore looks like minus something. And so you have to check for either of the components being bigger than 4. Clearly, if either the imaginary part squared or the real part squared is bigger than 4, the sum is going to be bigger than 4. So you don't need to add them together and check. So that's artifact. funny little circles out here, all weird round off stuff or some other kinds of errors. Probably some of that down there too. This all looks pretty good. You see, this was calculated in 52 milliseconds here. There's a requirement in the lab that you put the calculation time on the screen. Starfish. There's some interesting stuff. There is a student report on implementing a Mandelbrot generator on a DE1 board. You say, aha, it's done. Except Jurassic reused the name DE1. So this is not the DE1 SoC. This is just the DE1, which is actually a Cyclone 2 with an Atom chip on it. Intel Atom. So it does you no good at all. But there's a few other thoughts about calculating the Mandelbrot set. In particular, some theorems about it, which you may be able to use to speed up the calculation. You don't have to use HPS for control, but unless you want to, you do need the best HPS time for comparison. The corners of the region being plotted should either be displayed, either on the VGA or on the serial console. Obviously, if you're using a serial console, you're using the HPS. You should be able to choose the maximum number of iterations using serial input or toggle switches, or however you want to do it, but it has to be settable dynamically. Upon pressing key 3, the system should compute and display the full Mandelbrot set. We already talked about Busmaster. There will be a zoom interface using push buttons or serial communications or a mouse interface. It is sufficient to pick a center coordinate and zoom by in and out by a factor of 2. When you trigger the zoom calculation, all right, yeah. Oh, you have to be able to zoom in, out too. I'll just zoom in. But there's some edge cases. What happens if you zoom and what you specify is outside the region, the calculate region? What should it do?
Just display a black area.
You can display a black area.
It should not zoom and give you an error message.
You could not zoom and give an error message, although that could get annoying when you're being graded.
Display a bright yellow
Or
area.
what?
Could display a bright yellow area.
Or it could just say it diverges there also and do it the dark blue color. Make it the same color as the divergent because that's what it is. You know, like it sound a siren sound.
Right.
Through this, yeah, sure. If you zoom out, you have the same problem. What happens if you make a zoom out function and you zoom out more than the Mandelbrot set? You have the full Mandelbrot set, you zoom out. What should happen? It turns out when you do that without thinking too much about the arithmetic, you get lots of little copies of the Mandelbrot set all over the screen. It looks like a screensaver. It's kind of cute. Okay, we will talk more about this. Now, Friday. Friday is checkoff too. Is it useful to skip lecture on before the checkoff? Is that useful, or should we just do the lecture on Friday?
Skip lecture.
Have a choice, folks.
Skip lecture.
Huh?
Skip lecture.
Have lecture?
Skip lecture.
Skip lecture. Is that the majority? Okay, we're skipping lecture on Friday.